Okay, so let's look at some illustrations of numerical solutions of first order differential equations. And so here we have a differential equation y prime equals minus y, and we are given an initial condition that y of 0 is equal to 1, and we are interested in the solution over an interval going up to 2 starting with 0. All right, and so we choose different step sizes, and so we're going to choose step sizes that range from 0.2 to 0.1, and then reducing it one more by factor of 2, 0.05. And so the black lines that are shown here, these are the numerically computed solution, starting with the solution at 1, and then the numerical value. So the solution that is plotted, if you look at these graphs a little carefully, you will see that these lines are jagged. And so what has happened is that this plotting program has connected the numerical value. So we have one value at 0 here. Imagine that is drawn at 0. And then when the step size is 0.2, then the next time at which the solution would be available would be 0.2, and then at 0.4, and so on. And so those discrete values are being computed by the numerical solution, and a simple line is drawn. The red line in this plot is the exact solution, which is this e to the minus t solution for this differential equation with this initial condition. And so we can compare the numerical solution with the exact solution, and you can see that as we reduce delta t, so delta t being reduced, we're going in this direction. So the largest delta t is the solution which has the largest error. It has farthest away from the red curve. And then as we refine delta t, as we take smaller step sizes, we of course have to take more steps to come to a particular time. We improve the solution. The solution goes towards the red curve all along. And the departure of the numerically computed values from the red curve gives us a local estimate of the error, and we can quantify that error next. So we define the error norms over the interval, and so we've defined the 2 norm. So the 2 norm of error, it's in black on this curve, and we can then define the 1 norm, which is showing here in blue, and we can define the infinity norm, which is the max error anywhere in the interval, infinity norm. And they are plotted. So you may recall that we computed the solutions corresponding to the 3 time steps. We had delta t, we have taken 3 values, 0.2, 0.1, and 1/2 of 0.1, which is 0.05. And so we can plot them here. So actually what is plotted here are the numbers that we obtain with these step sizes. So there is a number here, there is another number at 0.1, which is here, and finally at 0.05 there's a number over here. And you can see that when we plot these norms, it's useful to plot them on log-log scale. So error norm is plotted on logarithmic axis here, and time step is plotted on logarithmic axis. And this is for first order Euler. And we have the behavior that the error is proportional to the step size to a linear power, first power. And so the slope on this log-log curve is a slope of 1. As we can observe, and all the norms are behaving in this way. And in terms of absolute error, the worst error that we have, you can see how big it is in terms of the values that we have plotted. So now we can contrast this to the solution we get by going to a second order Euler time advancement, and so we will look at that next. So we're going to look at the solutions obtained using the second order Euler's scheme, and they are plotted here. The solution is plotted as a function of time with 3 delta t's, and they're all very close to this red curve here, and the black curves and the red curves, you can't tell the difference very much. You see only red here because the red is the curve that I plotted last, and so that supersedes the blacks that are shown at the back. If you sort of zoom in, you might see them. And so basically errors are significantly smaller, even for, remember that we have delta t, 3 values, 0.2, 0.1, and 0.05, even for the value which is 0.2, which over this interval 0 to 1 at 0.2 means we have 5 steps going from 0 to here. And so with just 5 steps, and so total we have about 10 steps, error is already very small for the second order method. And so that's the virtue of this method, that at relatively low cost it is providing a pretty good solution. And so of course we can quantify the error. We don't quantify error by a visual plot. We want to quantify the departure, and so we can compute the error norms and plot that, and so that is what we will look at next. So here we are plotting the error that is obtained for the first example using the Euler second order scheme. And remember that the error norm, the 2 norm of the error, is plotted in black, and the error norm, which is the 1 norm, is plotted in blue, and then in red we have the infinity norm of the error. And note the logarithmic axes. Error is plotted on log scale here, and the horizontal axis is log of the time step, and this was for the second order Euler scheme, for which we expect error to decrease with time step with a slope of 2 on this log scale. So here we are seeing a slope of 2. So error is decreasing much more rapidly as the time step is refined compared to the first order method that we previously saw.